So I've got here a definition of the greatest common divisor of two numbers, right? And there's nothing particularly fancy about it, right? It's the same thing you probably learned a long time ago, maybe all the way back in elementary school, right? The greatest common divisor of two numbers is just the biggest number that divides both of them. Okay, so how can we find this? Right, well, back in elementary school, maybe 5th grade, maybe somewhere around there, you learned an algorithm. You learned a procedure for doing this, and it involves taking each of the numbers, writing out their prime factorizations, right? Rewriting them as the product of a bunch of prime numbers, and then you take the factors that they have in common, and you do something with the decimals, and out comes the greatest common divisor. And that's wonderful when the numbers are small. The problem with that method is that step number 1 is to find the prime factorization of the two numbers. And that, it turns out, is actually, from a programming perspective, from a computer perspective, is actually a pretty daunting task. There are no known efficient algorithms for determining the prime factorization of a number. In other words, sure, we can come up with an algorithm to do it. The problem is the algorithms, they aren't efficient, right? They in computer terminology, they don't scale. You know, as the number you're trying to factor gets big, the time it takes to do it becomes unacceptably large. Okay, so how can we do this then? Right? Is there a way to do this? And it turns out there is. There is a method for determining the greatest common divisor of two numbers that is efficient. Right? It doesn't rely on finding that prime factorization. Right? And that's what we're going to talk about in this lecture here. We're going to look at the theorem that tells us the algorithm, and we're going to prove the theorem. So it may not be immediately apparent, but this theorem here is going to give us the tool that we need to find these greatest common divisors efficiently. All right, so let's see if we can break this down here. See what this is telling us. All right, first, just to be clear, what we're trying to find is the greatest common divisor of two numbers. It's the greatest common divisor of A and B. Right? So what this theorem is saying is that if we rewrite A and B like this, and that may seem a little weird, right? But really, if you think of this Q as being the quotient of the two numbers, and if you think of this R as being the remainder of that division, that's all that's saying, right? Rewrite it as a quotient plus a remainder. Then this greatest common divisor that we're looking for is equal to the greatest common divisor of B and the remainder, right? What makes that cool, right? What makes it useful or efficient is R is going to be smaller than B, and B is smaller than A. So every time we do this calculation, the numbers that we have to find the greatest common divisor of, they're going to get smaller, right? And that's a good thing, right? Smaller numbers are easier to work with. Okay, so to see what I'm talking about here, let's actually work through an example. All right, let's say I want to find the greatest common divisor of 112 and let's say 3,260. Right, so what my theorem here says is, first I need to rewrite it like this. Right, now A is the bigger number, B is the smaller one. Right, so I'm going to say 3. So what I want to know here is, first, what is the quotient of these two numbers? Right, what is that Q? Well, if you ask your calculator, 3,260 divided by 112 is 29 point some decimal I don't particularly care about. That 29 is the Q. Right, so 3,260 equals 112 times 29 plus some remainder. And we're going to find that remainder easily enough. Just solve this little equation. Subtract 112 times 29 from both sides, and you're going to get R equals 12. Okay, so what is my theorem telling me? My theorem is telling me that the greatest common divisor of 112 and 3,260 is the same as the greatest common divisor of 112 and 12. Right? Because remember, right, to kind of map it back to that equation there. 3,260, this is A. 112 is B. 29 is Q, which I don't really use. And 12 is R. 12 is that remainder. Right? So it was B and R that became my new greatest common divisor expression. Okay, now I don't know, 112 and 12, I haven't really answered the question yet, right? I just broke it down to something. And notice, by the way, that these numbers got a lot smaller, right? A lot smaller. That 3,260 turned into 12. Okay, so, but obviously we're not done because we don't have the answer. So this is what's called an iterative process, right? In other words, I'm going to do it again. So now I'm going to say 112 divided by 12 is 9 and some decimal part that I don't care about. So 112 equals 9 times 12 plus some remainder. And again, I can solve for that remainder, right? If you subtract 9 times 12, 108 from both sides, you get 4 for the remainder. So what do I know now? Well, now I know that the greatest common divisor of 112 and 3,260, the number that I'm looking for, is equal to the greatest common divisor of 112 and 12, and this is equal to the greatest common divisor of 12 and 4. Okay, well now if you're a human, you could look at this and say, yeah, okay, we're done. The greatest, it's 4, right? That's the biggest number that goes into 12 and 4. But I want to bring this to an end that we can explain to a computer, right? That we can explain to an algorithm, right? Well, what's happened here is that we've gotten to the point where one of my numbers divides the other, right? 12 goes into 4. In other words, if I try to write out my equation again, I get 12 is equal to 4 times 3 plus 0. And if you're actually writing an algorithm, if you're writing this for a computer algorithm, this is what you're looking for. When the remainder equals 0, you're done, right? And at this point, the smaller of the two numbers is your solution, right? This is, in fact, equal to 4, and there's our final answer, right? Took, what, 3 steps, right? If we're counting that last one, right? If we're counting that last one, that one where we identify the answer, it's 3 steps, right? Much shorter than trying to find those prime factorizations, which would involve quite a few divisions, and fairly straightforward to explain to a computer, right? If you want to actually write code for this. Okay, so that's why this is a good idea, right? That's why we like this theorem. So how can we prove it? Right? How can we prove it? Well, this is going to be really the biggest proof that we've seen so far, right? This one is really kind of interesting. It doesn't just rely on, okay, look at the definition of divisibility, right? There's actually going to be more to it than that. And what really also makes this interesting for us is that we aren't going to rely on a definition to be the heart of the proof. We're going to rely on another theorem, right? This theorem here, the one that we talked about in the last lecture, and then you kind of look at it, well, yeah, okay, I guess that's interesting. This is really going to be the heart of this particular proof, which is why I went ahead and wrote it in here. Okay, so what I want to do, right? If I just kind of think about this at a high level, right? What I want to do is I want to show that every divisor of A and B is also a divisor of B and R, right? And then I'm going to show it the other way around. I'm going to show that every divisor of B and R is also a divisor of A and B. Right, so the divisors of A and B are all the numbers, let's not use A, are all the numbers on this list. And I know that these are also all the divisors of B and R? Well, if the set of all divisors of both of these pairs of numbers is the same, well, then their maximum divisor, their greatest common divisor, must also be the same. Okay, so that's how this proof is going to progress. All right, so let's see how we do this. We really have to do this in two parts, right? First, I'm going to show that if D divides B and D divides R, then D divides A. Okay, then D is also a divisor of A. So that's and because we already knew it was a divisor of B, that was part of our assumption there. That means all the common divisors of B and R are also common divisors of B and A. Okay, to do that, I want you to compare this expression here from the old theorem to this expression here. Right, and notice that they are the same, right? If I put Q in here for U, and I put 1 in for V. All right, so let's walk through that. All right, let's walk through that. So I know that D divides B and D divides R. My theorem says that means that D divides, let's put therefore, D divides BU plus RV for all integers U and V. Right, well, if it works for all integers, this is our universal instantiation again that I'm going to use here, thinking way back to our discussion of logic. Right, if it works for every U and V, then it works specifically for U equals Q and V equals 1. So let's put that in here. That means D divides Q times B plus 1 times R. Okay, but wait a minute. Come back up here to our original assumption. Our original assumption was that A is equal to QB plus 1R. Well, let's substitute. Right, this means that D divides A. Right, so what did we show? We showed that every common divisor of, I'll make sure I pick the right ones here. Every common divisor of B and R is also a common divisor of B and A. Okay, let's hold on to that. Set that aside for a minute. Okay, now I got to go the other way. Now I have to show if, and sorry, let me be clear here. This is what, because I didn't really label it. That's what I was trying to show, right? And I did down here in the end. Now I'm trying to show that if D divides A and B, then D divides R. And I'm going to do this practically the same way. Right? As a matter of fact, so much so I'm going to give you the first step here. Then I'd like to pause it and see if you can't talk yourself through the last part on your own. What I'm going to do is I'm going to take that equation, that A equals QB plus R, and solve it for R. Right? Move the QB over. This becomes R equals A minus QB. Right? Now, go ahead and pause. Or go ahead and pause the lecture. See if you can't finish it up from here. Right? Then you can turn it back on and we'll walk through it together. Okay, so remember, I'm assuming here that D divides A. Let me actually put this in here. D divides B. Well, if D divides A and B, then our theorem, 3.2, says therefore there exists, therefore D divides so now hopefully you're starting to see how number theory theorems, which may seem pretty abstract at first, can be used to solve very concrete problems. Now, in the next series of lectures, we're going to continue this theme by proving what's called the fundamental theorem of arithmetic, which says that every integer can be written as the product of prime numbers and that that product is unique. Now, again, this may seem very abstract, but prime numbers are extremely important in modern cryptography. And what this theorem does in practice is it lets us take a lot of number theory questions and reduce them to questions about just prime numbers.